So we reached the point where we want to talk about how do we help our students bridge their understanding of slope with the analytic concept of the derivative. The slope of the line is one of the earliest quantitative relationships that we teach students, but connecting it to rates of change and to limits requires new precision and abstraction. As teachers, we have to help our students to navigate this shift from finite differences to instantaneous change, as well as from geometric intuition. Can't write that fast. From geometric intuition to analytical reasoning. This really involves sort of helping students to reach new levels of abstraction. So what does slope mean when we're not talking about a linear function? As early as algebra, students encounter slope of a line as just a constant ratio of y2 minus y1 over x2 minus x1. In other words, they think about it as rise over run, or how much is your line changing in the up direction divided how much is your line changing in the sideways direction. This formula is describing a fixed relationship when we choose points on a straight line. In a linear function, it doesn't matter which 2 points you choose, right? Whether you choose these 2 points and take the vertical change over the horizontal change, or you choose these 2 points, take the vertical change over the horizontal change. The numbers themselves might be different, but the ratio will always be the same, because in a linear function, this relationship is global. No matter what 2 points you choose, the slope is going to be constant. However, when students apply that same idea to a nonlinear function, they can see quickly that the slope can take on different values depending on the choice of points. If I chose these 2 points, for instance, and computed the vertical shift versus the horizontal shift, the vertical shift is smaller than the horizontal. But if I chose these 2 points and take the vertical shift versus the horizontal, it looks like our vertical shift is greater than the horizontal shift. So this is no longer going to be a global feature of the graph, but rather it's going to be a local feature. It's one that's going to change depending on where you're looking at the graph. The concept of the derivative refines the intuition of slope as a way of locally describing the rate of change of a function. The derivative at a specific point x equals a is defined to be the limit of the slope of secant lines approaching that point. In other words, we say that f prime of a, the derivative of the function f at the point a, is the limit as x approaches a of f of x minus f of a over x minus a. And we can kind of draw a picture of some sort of continuous curve and think about an x value, specific x value a, and a changing x value of x, where this is our point x f of x, this is our point a f of a, and we think about the secant line as just being the line connecting those 2 points that are on the curve. As we vary x, as we bring x closer and closer and closer to a, that slope of the secant line is going to approach some fixed value, or it may approach some fixed value, in which case that gives us the instantaneous rate of change. So a local way of describing the rate of change of the function. The derivative generalizes slope to an entire class of differentiable functions, but this concept can be challenging for new students or students that are new to calculus because it introduces a new level of abstraction to the concept of slope. So the APOS theory, APOS, is a framework for understanding how students learn math through various stages of abstraction. So A stands for actions, which just means these are specific and external computations that are done to already known objects or to already understood objects. Right? So this is the most sort of basic level that doesn't require much abstraction because we're taking an object we already understand and we're just doing some sort of computation as practice. This can lead to the processes stage, in which internalized actions can now be completed without any external instruction. Completed without external instruction. So if we have enough practice on the action stage where we're just doing kind of basic computations, we're able to internalize that action a bit and be able to kind of interact with those things without sort of the external instruction, the step-by-step of it. When we're more comfortable with the processes stage, we can move on to the object stage. In the object stage, processes which have already been conceptualized into a single object can then be studied and acted upon. So if we've already kind of looked at various processes and conceptualized into the one object, that object can now be manipulated itself and studied and acted upon. This is clearly a different level of abstraction where we take a process and are able to sort of look at the process itself and now interact with that process. Finally, the most sort of abstract version of this is the schema stage. These are frameworks for linking together other actions, processes, and objects. It allows us to sort of fit the objects and processes that they're already working with into some larger picture. And see how they interact with each other. While we often think about these as a hierarchy of abstraction, students might not pass through the stages in a linear fashion. They might go back and forth, right? They might sort of go from an action stage to a processes stage, but then when a new topic is introduced, they might have to go back to the action stage of something that they've already understood more abstractly and work with it in a more concrete way in order to integrate a new idea. So it's not always as simple as just linearly working your way through these stages. But let's talk about it sort of in the context of this rate of change idea. So in the first stage of understanding, a student's going to perform specific step-by-step calculation in order to find the rate of change, typically by following a learned formula without any deeper conceptual understanding. So in this stage, students might be given a linear function either as a table of values or an equation or maybe even a graph, and they're going to find 2 points on the line or find 2 points from the function and compute y2 minus y1 over x2 minus x1. That action is external computation for the students to practice without necessarily being able to interpret what the results actually mean. Once students have conceptualized this, they can move on to the processes stage. So the processes stage, they might be able to mentally perform the calculation. They can imagine varying the inputs, so mentally perform a calculation. They can imagine varying inputs and think about slope in a more dynamical way and visualize the change occurring, right? So if you changed your inputs or your output, they might be able to get a better sense of what's happening on the graph. So at this stage, students can understand slope not just as a formula, but as a relationship between two changing quantities rather than just some real number computed from points. So they can understand the relationship, they can understand slope as a relationship between quantities. Right, so at this stage, maybe they might know that, a line like this is going to have a smaller slope than a line like this because our second line has greater vertical change for the same amount of x value change as the first line does. At the object stage, the process itself becomes an object of thought. That is something that can be analyzed, transformed, and related to other objects. So at the object stage, we hope that students can see slope as a property of a line, something inherent to the line's representation, not just a computation. And then once students reach the schema stage, they'll be able to integrate their understanding of slope, rate of change, and derivative into a coherent and flexible network of concepts, right? So we really require a new level of abstraction in order for students to see the relationship between slope of a line and the instantaneous rate of change, right? The local property of instantaneous rate of change of a function. So we hope for them to recognize that slope's a specific constant rate of change for linear functions, and that rate of change is a generalization of slope which can vary. That the derivative represents the instantaneous rate of change which unifies slope and rate. So by doing that, they can reason about new contexts like motion, growth, optimization, using interrelated ideas. At any given time, students might be at a different stage, and knowing how to scaffold your instruction in order to support students from one stage to another is challenging, but an important skill for teachers. So let's think about one way that we can try to do that. Before we define the derivative rigorously, it can be useful to study the function that gives the slope between the secant lines between 2 points. To that end, we're going to define the function s sub a of x, which represents the slope of a secant line connecting the fixed point AF of A to some varying point XF of X. I sort of drew this picture earlier. Let's say this is the point AF of A, a fixed point, and then we have some moving point, which we'll call X, F of X here. So this S sub A function, S sub A of X, is giving us the slope of that line. I'm just going to say n sub green to mean the slope of the green line. It measures how the function changes from x to a. And when we graph s sub a of x, we can observe how the slope of the secant line varies as x approaches a. If the values stabilize near a single value as x approaches a, then that value is the derivative, f prime of a. So examining s sub a of x provides a bridge between the geometric reasoning and then the analytical definition, right? This can help students go from one stage to another in their abstraction and their understanding of that. So let's look at an example. If we take the function f of x equals x squared and we take the fixed value of a equals 2, s sub 2 of x is going to be the function, so remember it's f of x minus f of a over x minus a. In this case, f of x is x squared. F of a will be f of 2, so that'll be 2 squared or 4. And x minus a is just going to be x minus 2, because a is equal to 2. And we can kind of say, you know, we can use some algebra here to look at this and say, as long as x is not specifically equal to 2, this is just going to be equal to x plus 2 when x is not equal to 2. And so as x goes to 2, s sub 2 of x will approach 2 plus 2, which is 4. And it might be helpful at this point to actually give students like a picture to look at, right? So if we take s sub a of x to be the slope of this line here, so this is our, I can't write on here, but this is our s sub 2 of x. It's going to be the slope of this line connecting the point 2, 4 on the curve to some other varying point x sub f of x. And as we move that point closer and closer and closer to 2, that slope's going to be stabilizing at some particular value. And you can see that if you actually were to compute this using the tools of GeoGebra, you can see that that slope's going to be approaching that value of 4. So secondary teachers might interpret slope as a static property, secondary students can interpret slope as a static property rather than something that depends on a chosen interval. And teachers can use dynamic graphing tools like the one I just did, or maybe tables of difference quotients to illustrate how secant slope changes as intervals shrink. Students often encounter the following challenges when they're trying to kind of make sense of this. They might treat the difference quotient as a formula rather than a process. right? They might be trying to just come up with a numerical answer rather than thinking about the concept of taking a point, getting closer to some fixed point. Students can also confuse slope between points on a line versus slope at a point. Right, so they might have that difference, or they might have trouble differentiating between instantaneous rate of change versus an average rate of change when you're looking at a nonlinear function. They might have trouble believing that continuity guarantees differentiability, or they might believe that, which is the problem, right? Believing continuity is going to imply differentiability. And then misinterpreting the derivative as speed without understanding the limiting process. Speed or velocity. Without understanding the limiting process that gives us the derivative. So in order to connect these issues to our classroom practice, things that we can do to help students would be using visualizations to show secant lines approaching a tangent line. We can emphasize language that distinguishes between average rate of change and instantaneous rate of change. So for instance, making sure we always talk about average rate of change when we talk about secant lines and instantaneous rate of change when we talk about tangent lines. We can ask students to articulate what happens as x approaches a and why it matters. So ask students to explain what they mean when we say x approaches a, and then probing that to see if they have any misunderstandings. And finally, providing opportunities for students to predict or estimate and then refine slope approximations. This helps students to sort of help bridge that gap between the more concrete actions and processes stage to the more abstract object and schema stage. Predict, estimate, and refine their slope approximations. So all these things are important when we're helping our students to move to a higher level of abstraction.